Welcome. You are right on time, Tori. Good to see you here in the cold world. Welcome. You are right on time, Tori. We don't want to listen to that past me. Now it's officially. Let's put past. I am not cut out for certain.
You're watching yourself and like figuring out memories that you didn't have.
The short answer is yes, of course. I'm not an. I mean, I'm cursed with enjoying being the center of attention as part of my personality. But that doesn't mean I want to like look at myself 3 seconds ago, right after things happened. That's weird. Yeah, when you're looking at yourself 5 seconds ago or 10 seconds ago, that is freaky. Oh, all right. Hey,
Job, though. Want to be the center of attention.
who knows? Maybe I do.
I really want
I do like to play music too. I went to karaoke last night. I'm fine. I'm good. I will never become a rock star, but I do get chances to, yeah, perform and have fun. All right, team.
that. Yeah,
Billy Joel. That's one that will often get lots of other people singing along too.
that's the best part.
Lovable.
You're
Yep. The karaoke song that I sang once that was the most surprisingly crowd singing, like generating of all the people in the place was Dreams by Fleetwood Mac. Yeah. But it just like that place I was that one night, everybody just was like the first verse, someone with like charisma and like three friends was like loves that song, started singing, and then like by the end of the first verse, the whole place was singing that song. It was pretty fun. And so I was just barely, I mostly listened. That was fun.
Professor by day, rockstar by day.
Professor by day, hobby musician by night. Person who likes to do music for fun and no money ever. Yeah, by night, exactly. All right, hey, welcome. More folks are arriving in the Zoom and in the Sylvania campus room, as you can hear us chatting here. Welcome to Maria Lisa. Welcome, Quincy. Great. People are showing up. All right, well, let's give it another, I don't know, half a minute. Hopefully we'll get a couple more folks as we dial into class stuff. Let's share. Oh, dang it. Did I forget to share? Beginning of this video is just going to be the worst beginning of any video. There you go. That looks better. There's a nice screen. Nice thing to see on the TV. Our class, we're here. Um, let's just start with a brief little quick reminder for everybody. I'm doing my best to keep up every day with feedback on your homework as it arrives. Remember what you get back from me immediately, like when I see you've submitted an assignment, I give you your money, I mean your points, so you can, be working for the credit that'll earn you. I hope the most pointy letter as a grade at the end of the quarter is my goal for everyone. But more importantly, your homework's for your learning. And so I do give you back along with your, I think it's 3 points per assignment. I give you back, I just drop in some ideas I have about the topics we're learning about there into the comments. Those show up in your grades as well. It's just one more place to just, I don't know. We've had a discussion in class, you've done some work, you've asked some questions. And this is one more place to look at the ideas on each assignment. Some of the little notes are like a sentence long. Some of them are like, I don't know, like a half a page. Just depends on what the topic was and how much was on my mind when I wrote the note. I edit them every couple quarters to keep them current or if something changes, but they're just one more chance to think about the ideas in each section. So I recommend checking out that feedback. People are also, we have flexibility in this class with like due dates and stuff to accommodate people's lives, and that's a good thing. So wherever you are in your work, just be sure you're getting into that rhythm of fitting our classwork into your life schedule. Some folks are like, every assignment's coming in like the day we talk about a section, I'll see their assignment that day because that's their rhythm. Some folks haven't quite gotten even started on some of the homework yet. Maybe they have complicated things going on. If anything is complicated enough that, our midterm is in what, 2 weeks, 2 weeks, 2 weeks? If things are complicated enough in life that the midterm is coming and you're like, oh, I haven't gotten much of that homework done. I got to think about things. If things are complicated and things are going slowly, reach out as soon as possible. And that way, if we need to, we can strategize and I can support you and your learning and also you and, getting work done and succeeding as a, pointy letter or, about the other good letters. Any of the three cool letters are the ones I like for your grades, but most importantly, that you're learning stuff and that you're, getting the support you need to learn. So reach out as needed when support is something that you might need. I'm here to help you out. Any questions just about those boring or interesting details, depending on your perspective? No? Okay, mellow. Yeah, and just keep your work coming. And don't forget, when you do upload an assignment, let me just show you an example. One of the bonus place as let's say today is a class day, we probably have an assignment due. Yeah, so the work from section 6.1 is due. So if you're uploading your work, you've got it all either written out and like you've made a scan or a picture of it that works for uploading, or you've typed it up and you're uploading your file, you've added your file here, and as you're adding it, you're like, that one question, whatever, 611 if you're in the PDF or whatever it was, number 15 if you're in the ebook. We didn't talk about, I forgot to ask about it in class. I've got it written up, but I'm just, that result in the back of the textbook and my result, right here, you can just say, hey, Ralph, please look at, and then you can just tell me whatever you want me to give you some detailed information or feedback on. And then when you get your grade, you'll also get, you'll get all the general feedback I would normally share, but above that, at the top, I'll say, great question. And, look at your work and address your question. If it's possible to type it up briefly, I will. And if I'm like, oh, that's actually kind of a complicated thing, then we'll probably just talk about it in class, or we can set up a time to talk together outside of class if that works for you. So don't forget, those comments are a great place to also get some feedback as we work. Cool. I'm not going to submit my nothing. All right, it's cool. Great. Okay, and now let's get back into our discussion. We left off last class. We were talking about the difference of two proportions. We talked through the basic ideas. There's a little more to discuss. Want to pick that up right here, and then once that's done, like reset with a little maybe questions about homework, or start with homework questions first if there's something burning on your mind, in your mind or heart. Any preferences? Any questions, I guess is what I'm saying. Are there any questions? Yeah? No? No, yes. Okay, great. Well, then you're in the world of like getting that worked into your regular day-to-day life. The more it's worked day to day, the better. I just find that rhythm. I don't see anything in the chat. Let's just go back and look at these two proportions things, see where we left off, and continue the discussion today. Welcome. All right, cool. We're back. Talked about a lot of this stuff last class, these differences of two proportions. Let's kind of just remind ourselves together where we left off. We looked at this long example based on a data set where people around the US and people at Duke University, the home of our textbook, were asked about kind of their feelings about the global climate crisis. We learned about thinking about the difference between two groups' proportions as something that might be of interest to researchers as a parameter and something we can always estimate with sample data. We talked about confidence intervals and hypothesis tests for this situation in a lot of detail. So let's just kind of cruise through that detail at hyperspeed. We saw a lot of stuff. Whew, yeah. Any questions about this as you're working on your homework, just let me know and I will help you out. And then we got through that pooled estimate stuff. Yeah. See, my memory's working medium well. We talked about this hypothesis test. Remember the satanic proportion 666? That was pretty cool. I recently watched a video essay about Satanism. No one believes in it, is what is what I learned from the video. No one believes in Satan except for like some Christians, because that's part of their Christianity and beliefs in certain parts of Christianity. All the satanic stuff is just, it's just for fun, turns out. In any case, sorry, But again, like we said last class, goats are fun, so that's good. Okay. Yeah. Yeah, we talked about that. Wait, no, did we just get through that calculation and that's where we left off? Is that the end? And then we were like right here? Is this true? Anybody with a good memory? I didn't look at the video. Am I right? Well, let's start here because I don't think we talked about this in detail. Let's talk about this slide right here. We have a null hypothesis in the situation from last class that there is no difference in the proportions of Duke students and the proportion of people around the states, US residents, who are a great deal concerned about the possibility of the polar ice cap melting. And the hypothesis test gives us a p-value of 8300. Yeah, I didn't say that last class. I can remember now that I'm reading it out loud. Okay, just knowing that, we're right here at the conclusion step of a hypothesis test. Question A, what is the meaning of the p-value? What does it mean in terms of a number? And would we reject our null hypothesis at what is about the highest significance level you're going to see in day-to-day life, Greek letter alpha, significance level 10% or 10/100ths? What do you say? Either question, you can take them in either order. One of them, I think, is less complicated than the other. This is the big one, one of the two big ones in the world of hypothesis testing. Well, it's the likelihood that if our null hypothesis assumption is true, if we assume it's true, so if we assume no difference in these proportions, that's how likely that just any old random samples as big as ours would show up with at least as big of a difference as we see. Kind of it's a big mouthful, right? It's a big mouthful. So yeah, shorthand, the likelihood that it would happen again if it is finding samples this size in a world where the null is true and getting at least this big of a difference, the it does a lot of work there, right? So it's tricky for us to build that it out in our language and really our whatever working knowledge base this quarter, especially while we're working hard on this, to blow that out into the biggest personal, sentence. At the end of the quarter, you probably have to write it down or type it on your final exam. But it really is that's the trick, that challenge. So I mean, that's what we're talking. We're talking about the meaning of the p-value, right? So we're there on bullet 1. Does that feel good to people, that description today? Okay. Now I've spoken too much. Are we going to reject that null hypothesis that there's no difference in proportions of Duke students and US residents? No. Specifically, why not if you're looking at bullet B, or sorry, the second bullet? Yeah, well, we don't have strong enough evidence to reject the null hypothesis because our p-value of 8300ths is way higher than the necessary significance level of 10/100ths. We would need to see no more likely evidence. It is hard to say all these things out loud. We would need to see a big enough difference in our sample that it would look less than 10% likely under that assumption of no difference to have strong enough evidence to say we're going to reject the null in this setting. God, it really is hard to say these things out loud, but maybe we should have like a talk about p-values out loud practice party day. Yeah, catch up and review day, but not like everybody in front of the entire group. We'd break up into little teams, think, pair, share style. Maybe we're getting one strong vote against the idea, but I respect that already. But somebody like one vote for the idea. It could be optional. People who just want to think and not share can just do that. Yeah, I'm never going to pressure people into situations they don't want to be in. That's just unkind. But some people, it's tricky. How do you do this job? So many people with so many different needs. Okay, so how do we state a meaningful conclusion here? We've talked about the big ideas. if you were just going to write down your meaningful conclusion, that just means that you got to indicate what the evidence says about the null hypothesis in the context of the study. What sentence would you write down if that was, say, like a homework problem, and that was the last question on there? Just for practice, take a minute or two, type it up or write it down, however your note style take is. And then if you're out in the Zoom world, share it in the chat so we can enjoy it. If you're in the room, you can share and let me know, or I can come visit, and just we'll get a sense of your styles. You're like your literary / statistical analysis style. Because me doing that as an example is only so helpful so many times. I can always show you mine after. I'll type, maybe I'll type one in the chat too, and then after I see one of yours, I'll share mine. And then we'll have one of the slides, we'll have at least three or four if more than one person shares. 5, who knows? Um, It's writing down the context in plain language that's the hardest thing, just getting the thing into a sentence. Like I've already been backspacing in my, oh wait, that's so many people do. So like in research journal articles, people didn't hear that question maybe on the mic. It's, do we need to include the p-value in the conclusion? It shows up often in research settings, though in day-to-day life, you may or may not feel like that's necessary. I'd say in stats class, you want to indicate how you used it in stats class because it's kind of like we're in a research setting. Like when I share mine, you'll see how I do it. So what have I got? We don't blah blah blue. That the oh, I've got one. I'm just gazing and staring into the chat window, waiting for one for you from you all. Or if anyone has any ideas in the room that they want to say out loud or just share, I can visit. Hey, look at this. As I dream of something in the chat, there we go. Thank you. Okay, Lauren R. We fail to reject the null hypothesis. Straightforward statistical statement, classy, that there is no difference in proportions of Duke students and US residents who are a great deal concerned about the possibility of the polar ice cap melting. That's the huge mouthful that communicates what the null assumption is. Well written too. It, unsurprisingly looks a lot like the statement above, just written in the context of this conclusion. And then, ooh, with 90% confidence. That's one way to say you've got a significance level of 10%. And then here's my alternate version that I just typed up. I just had to return on my chat. I started with the p-value stuff. So like Corey's question, I would go, we don't have statistically significant evidence. And I'm just saying, P equals 83/100, bigger than 10%. That to a nerd, that would indicate the significance level was 10%, kind of equivalent to Lauren's 90% confidence, but different style. We don't have statistically significant evidence against the assumption that there's no difference in the proportions of Duke students and US. I forgot to type the word residents, who are greatly concerned about the effects of the polar ice cap melting. Yeah. Oh, hey, cool. Another example focusing on the meaning of the probability coming in from Quincy. It is 83% likely that the results of this study would be seen again under the same parameters. I might go assumption, but let me, I didn't finish reading though. With a significance level of 10 hundredths, we fail to reject the null that there is no difference between the Duke students and US residents. Yeah, that's well written, Quincy. I just changed the word parameters to assumption, or assumption and parameters, because I think parameters describe how the research is done, which is how you get the sample data. You just want to make sure it's all about the same assumption as well. A little tricky. I'm just being as technical as I can because your writing is good, everybody. Good work. Okay, that's 3 examples. That's pretty great. Let's see what the slide says, something similar. Oh, nothing. It says nothing. So the YouTube's got the result if you're looking at these slides in the future. YouTube's got all that stuff, hopefully with good closed captions. If you want to download the transcript and get it written out, bang, good old download transcript on the YouTube videos if you want detailed notes with only a few mistakes. Technology good sometimes. That is cool. Okay, so comparing 2 proportions, basics, we're just in 2 large groups. Population 1's proportion, P1, take away or subtract away population 2's proportion, P2. That's the population parameter. For a point estimate, the symbols switch to P's wearing little hats. So P with a little hat, group 1 is the sample proportion from group 1. Subtract away the sample proportion from group 2, P with a hat, subscript 2. Talked about the conditions last class. The crucially important condition we always consider is independence of the data set. That applies to each sample individually, so no member of one sample's outcome should impact directly any other members of that sample. And of course, between the 2 samples, there shouldn't be any relationships between any members of both samples. As long as everything is random, that's great. In the sampling process, it works out with random sampling. Otherwise, just convince yourself that it's true in situations with other things. At least 10 successes and failures in each group is the crucial sample size condition to check using the estimate from if you're doing a confidence interval or using your assumption proportion if you're doing a hypothesis test. Whew. Standard error has a complicated formula, but it just depends on the proportions in both of the groups and the sizes of both of the groups, with some, multiplying and dividing and adding and square roots. It's enough work that, double check if you're doing this stuff by hand, double check your calculation when you're using your calculator or computer. It's easy to mistype that thing. If you miss like 1 parentheses somewhere as you're typing all this mess out, you can just get a weird, crazy number. Or if anything slips out from under the square root, things go absolutely haywire as well. So be careful, or just use, GeoGebra or any technology you prefer for calculations, because when you do that, you can get the calculations done quickly and accurately. Cool. Here's a reference slide they made for us to just collect these little formulas somewhere. Yeah, and that important note, if you're focusing on the calculations with the formulas for hypothesis test, use your assumed proportion from the null, and again, use the sample proportion P with a hat if you're doing a confidence interval. Crucial. And you can see the similarity and differences between these formulas for this proportion stuff right there in the standard error row. We're going to get to these mean formulas in the next chapter, so that's just a little preview. Don't worry about that yet. Top row there. Not yet, not for us. Yeah, cool. Okay, and that's the end of that section. All right, groovy. Good work. Good practice with those conclusions. Did we do the little quiz last time? Did we? Let's go look. Because if not, it'd be Great, we got the answer. Thanks, Quincy. No. And there it is, the creatively named difference of proportions quiz. I came up with the name myself. Let's check it out. It could have, maybe it would have been better last class, but let's do it today. Starting the quiz. Here we go. Oh, great. We just talked quickly through a lot of the topics from last class on those recap slides. So these are there somewhere. What are the conditions for using inference techniques to analyze the difference of proportions between two, I should have put independent groups, separate groups. First, each group must be composed of independent observations. Second, the two groups must be independent of one another. Third, both groups need to be big enough for the analysis to work. That's 10 or more so-called successes and failures in both the groups. Or last, all of the above. Did people hear Tori in the back row through the mic out there in the Zoom world? Is the mic that good? All comes back in the chat. Boom, it's in the Zoom, it's in the room. It's all the above. Just three things to check, just slightly more complicated than the conditions we had for one proportion estimation or hypothesis testing. So just grab that, all of the above. That's your point for our discussion last class and, the beginning of this class. Get it. And don't forget to submit the quiz to make sure you get full credit for your participation, listening, thinking, and all the good stuff, right? Yeah. Cool. All right, team. Let's cruise into the next section. That's the plan. Like, there's nothing else on the calendar but getting into that next section. Let's go. Well, maybe we should double check that. I remember all those times I forgot to talk about the interview part of your project before. Let's double check that I'm not forgetting something on the path to the new topic. Where's our main page? Oh, got to get out of the quiz. Bye, quiz. I don't need a point to school. Go look at the schedule just to make sure I'm not making mistakes again. Our next topic is going to be testing for goodness of fit using a Greek letter, chi, or chi, if you are a Greek scholar, depends, square. We'll open that up in a sec. First, I just want to peek at the course schedule. Come here, friend. Hey, good. Okay. We did talk in some detail at the very end of class last time about these get started ideas. I've already seen like one person's interview subject and plan. Something came right to mind for them, like right after we had the discussion. That's great. If you have any questions about getting started on this stuff, let me know anytime. And maybe like, we didn't talk about the guide to everything, so we'll probably talk about that. Let's talk about it right after the break. So we'll do after the break so we can make sure to get a good chunk into this chi-square discussion first. Don't let me forget after the break, a little more guidance on your project work. Because I will forget, because I am tired. I did go to karaoke. It was the person who owns the bar's birthday, so it was really fun. Everybody wanted to sing her a song she likes, and she grew up in the 90s. People like stuff from the 90s. It's fun. Sure. And then, of course, right after I say I'm tired, I stare at the computer, just confused. We're going to slides for the next section. Goodness of fit, chi-square. Here we go. Testing for goodness of fit. That phrase should not be familiar to you unless you're familiar with this technique. We'll make it clear what it means as we go along. And chi-square is the name of a statistic, the name of a test statistic that we will see what it's for as we go through the discussion. There's no reason to try to explain this complicated phrase without context of a study. So let's look at one. Ah! Yuck! Ew! Ew! It's icky, grody Walter Frank Raphael Weldon, a gross monster. When you see that phrase like on Wikipedia or a slide from a statistician, Walter Weldon here is described as a English evolutionary biologist. That's the phrase that modern assholes, pardon me, racists, I mean, eugenicists. It's the phrase that modern people who don't really want to take the time to understand the horrific impacts of eugenicist thinking on the world That's the phrase they've started to use to call the founders of modern eugenics. Do people know what eugenics is? Do you know what that is? So we get no's and we get yeses. It's basically the idea that you can use science to hierarchically rate people. You can measure our intelligence, and some people are going to be brilliant, and some are just going to be stupid, and there's nothing you can do about it. And any other human trait, any other, but intelligence is where they focus their work, and they also spent a lot of time showing correlation between intelligence, for example, and the various racial backgrounds of human beings, assigning high intelligence. Gaze into the evil white eyes of icky Walter there. You might not be surprised they said that white guys were the smartest. And they said it again and again and again. And their work led to things like the Jim Crow laws here in the United States, horrific practices by fascist governments in Europe, including all of the Nazi war crimes and the Holocaust. The great horrors of our modern times were justified, I'll put it in quotes, scientifically by asshole fuckers like Walter Frank Raphael Weldon. So if I could go back in time and punch him right in the face, I would. Much like if I could visit the office of whatever Twitter's called now, whatever that's called. If I could go there and punch that guy in the face, I would. What's that? Yeah, he's a modern, he talks about the same ideas along with going ahead and showing his enthusiasm for them with the hand gestures of the ugly monsters of the mid-20th century. So Elon Musk would think Weldon's a genius and would use his ideas to justify his own ideas. Whatever, like neonatalism is one weird thing. He wants to have a lot of kids because, well, guess why? Boy. In any case, a lot of these monsters, like also like this biometry, that whole, it's a pseudoscience that is the eugenic study of measuring people's traits, some physical, but many cultural or standards of things like the IQ test were developed by these bad guys. Francis Galton and Carl Pearson are the other two very famous, very evil monsters from that early time of statistical study in England mainly. What bad boys. They really wrecked the world. No, in any case, they also were total nerds, and their ideas about statistics, the way they analyzed data and their math skills were well skilled. So like the ideas they used are still used for data analysis, and examples of when they did things that were not horrifically racist or horrifically sexist or horrifically classist or combinations of the three still are here in our textbooks with no context about their monstrous never-ending crimes. Can you see why I didn't try to write one more slide? That would have been a long slide if I tried to write it. I'm not that great of a writer. But look into eugenics as a history. Check out what sociologists have to say about it. They know the most about the ongoing impacts. In any case, they also just did nerd stuff. Like in 1894, this monstrous proto-Nazi, that's how I would describe a eugenicist. They're proto-Nazis. He rolled 12 dice. As you can see, he also had a lot of focus. He rolled them 26,306 times like a true nerd and recorded the number of fives or sixes, which he would mark as a success. His idea being the way dice were made then, it's a six-sided die and all the little dots were like carved out. And he had this idea that, well, when the sides of 5 and 6 have the most carved out stuff, so maybe they're the lightest sides of the dice. See what I mean? Like, because on the other side is one carved out thing from 6 or 2 carved out things from 5. So there's more air up with the 5 side than the 2 side on the die. His idea was, well, I think maybe that'll play out. Those should be a little bit, the lighter side should come up more often, because the heavier side should go down, thinks the proto-Nazi. So he rolled his dice to see what would happen, right? Weird and interesting nerdy thing for a bad guy to do. Okay, here we go. Let's see what happens. Okay, in 2009, Zachariah Labby from the University of Chicago, a fancy university in a big, fun American US city, repeated Weldon's experiment. He's probably a stats graduate student. And, you know, when people learn the history of famous experiments, sometimes they think, that sounds neat. So let's just assume Labby is just a nerd. Let's not assume anything about his ideology other than he likes dice, okay? Because we don't know. Although when I look at him, I'd like to see his Substack. Sorry, just saying. In any case, he built a little machine. He has a little cool machine he built so that he could do the same kind of experiment and just he could roll 12 dice at a time, take quick computer images of them and process them. There had to be some manual processing to do counting and to do a recording of the data set. But unlike in Weldon's time, you know, long before computers, Labby has modern computing to help him store his data and analyze it. So instead of it being, doesn't say how long it took this horrific monster to roll his dice thousands upon thousands of times. I'm guessing maybe it was like his just thing to do at the end of the day for months, probably. It would take me months to do that if I didn't have a computer to help me. Labby was able to get it done as far as the data collection in 6 days, like a week. Go computing, go, go, go. Oh, look there. Look there, look at that. Galton, that's the name of one of those horrific monster proto-Nazis. They still call their school of statistics after that guy. And when people say, excuse me, let's change the name, the people who work there go, well, you just don't understand biometry and evolutionary biology. He's there. That for their time, they weren't that bad. They were bad. There were cool people back then, too. All right. Okay, now, unsurprisingly, over 100 years after Weldon's experiment and using completely different dice. I mean, unless they happen to have at that university historical dice collection. I don't think they did. But using probably just the dice you'd get like with Monopoly games or other board games you might get at the grocery store, or sorry, the department store, Target. He didn't see the same phenomenon as Weldon. That's the higher frequency of 5s and 6s. That didn't happen. So he went ahead and did more data than Weldon did in the olden times. Because once he got going and he was processing data, he's like, wow, I can do so much so fast. So he has a huge, and instead of recording in his data set just when 5s and 6s came up, he was able to record every single outcome, all the die values on all the dice he rolled throughout his week of data collection. So, little complicated probability question to just think through, maybe medium complication. Let's just talk through it. So Labby ended up rolling his 12 dice 26,306 times, same amount of rolls, I think, as Weldon. Right, is that right? Yeah, selects the number, I guess. But then recorded each time which of the dice came up 1, 2, 3, 4, 5, or 6. So for any individual face of the die, how many times, like in this picture, it's a 2 that has come up on the top of the die. How many times should he have recorded a 2 if the die were perfectly fair and the odds played out, or probabilities played out exactly? And we can just look through these and see which ones are wrong and right and why they have some good ideas and some bad ideas if you want. Or you see which ones are kind of wrong? Or do you want to just talk through them? How's your probability feeling at 9:40 on Thursday? Was that a D? Ding, ding, totally. Because just think about it. 12 dice have been rolled thousands upon thousands of times. Well, there's the 12 dice getting rolled, multiplied by the thousands upon thousands. And then just, well, that's how many total faces came up. Divide that by 6 to knock it down to one face. And you get this big number, 52,612. And you can see they just chose like little bits of that calculation for the A, B, and C options. And of course, they put them first to kind of distract people in the multiple choice process. But there's good ideas there. The 1/6 is an important number, right? Dividing the big number by 6, that's important, but you kind of got to put things together. The 12 is important. They're all important. Yeah, but over 52,000 expected appearances for each face in Labby's dice rolling experiment. Cool. And these are expected counts. put a star by the word expected, right? We're imagining if the probabilities play out perfectly, what would we expect? What would we expect? Expected. Okay. It's an important part of the tale here because it's going to impact all of our work in this goodness of fit world. Okay, there's his results typed out with that expected value the same 52,612 to the number would be perfect probability playing out over the course of the whole experiment. That's in the expected column, the third column there. Labby's observations are there in the first column, and you'll notice they're also in the graph, graphed not using the huge numbers in the 50,000s, but using the proportion of times each face of the dice, each of the faces of all of the dice came up. You'll notice that the graphs zoomed in to like, reading graphs, especially when they're on a slide that you might be seeing on a small device. Let me just give you a couple of things I noticed about this graph. It starts at 16% and it only goes as high as 17 4/10%. So that's a really small range in proportions, right? The expected, there's the 1/6 is between 166 and 168 after a decimal. That's 1/6 that line. And you can see there's his result. The side of the die with 1 pip and the side of the die with 6 pips came up just slightly more, like slightly more than expected. And then the remaining sides, 2, 3, 4, and 5, came up slightly less proportionally than expected. You can see the observation numbers varying. What's the lowest one? Is the 2s is the lowest number. That's 52,118. That's like not even 500 fewer than expected. 2s coming up. I think 6 came up even slightly more than 1. That's 53,285. That's not a whole 1,000 more than you'd expect, right? So on the scale of these hundreds of thousands, if you add up all the numbers, it's 315,672 total die faces recorded in his experiment. The variations are on really small scales, both proportionally and numerically, when you think about how big this data set is. What do you think? Do we have evidence that, how do I phrase it? His expected counts, if we assume the die is fair, do we have evidence from his data set that it's actually not quite fair? Well, that's the question he's asking. So let's go look at that in more detail, because now we've got all the setup. Here's I think it's on his slide. Yeah, and intuitively, Quincy's got the same intuition as me. Data looks pretty fine, like they're not that far off expectations, but the thing is in statistics, remember, sometimes a tiny difference here, like these really small variations in proportions to you and me, people who are just going to go play Monopoly or Risk or whatever. Why did I choose the most boring 2 board games? We would play the good one, Yahtzee. We would play Yahtzee, the best dice game. But I don't care if the die is perfectly fair as long as it works for Yahtzee, right? Though, well, we'll see why on the scale of hundreds of thousands of things, big sample sizes even make small differences look statistically significant. So our practical, we don't care about that little variation. Let's go see if this is statistically significant or not when we have a huge data set. And there's lots to talk about on that path, because yeah, so we've already asked the questions at the bottom of the slide, just in Ralph E's instead of in slide E's. And you've answered them well. Good work. Oh, by the way, all the slideshows say on the first slide, edited by Ralph Yutz, Portland Community College. Every picture of dice in these slides I got from a Google search, Google image search that said I put in dice, and I picked the ones that I thought looked the best. So if you like these dice photos, just remember, I'm working for you. Dicing up your slides a little bit. Okay, do these data provide convincing evidence of an inconsistency between the observed and expected counts? Complicated way to phrase the same question we just talked about. Practically, who cares? But statistically, with a huge data set, well, a nerd will care. And there's other situations on Earth in research where you might have expectations about something you're counting, and you've got a data set that's, whatever sample size you could actually do in research, that's not 300,000 plus, but you want to see if your observed values, your observed counts fit your expectations. Is your observation a good fit? Do we have goodness of fit? See, we got to the name of the section. The question's about do our observations fit our expectations? This is called goodness of fit. So here, spelling out these null hypotheses, it would be, let's assume for a null hypothesis, no inconsistency between observed and expected counts, that variation away from 1/6 in the data set is just random. That is, Labby has a fair set of dice. Cool. Yeah, and alternatively, well, we can see in the data set there is a slight inconsistency if you zoom in on the proportions or you just look at the numbers between observed and expected counts. That would indicate the observed counts do not follow the same distribution as expectations. That meaning there would be bias in which side comes up rolling Labby's dice. Good old dice. Yeah. And it's kind of a nice one, like the nothing's going on here for the null hypothesis is just the variations random. It's just not an indication of something other than you expect. Evaluating these hypotheses. To evaluate these, and that means research communities who developed these techniques in the late 19th and early 20th century, had to learn to quantify how different observed counts are from expected counts and quantify it in a way that takes randomness into account for reasons of doing probability, p-value calculation stuff. So there's like a lot of slides here about how this chi-square statistic works. They're kind of interesting, but when we get to just how to do the calculations, it's complicated enough that we're going to do, I will never not use a computer for these kinds of calculations because even when there's just a few categories, like here, there's 6 sides of the dice, the numbers get kind of hairy to push around on paper, I'll put it that way, or type into a computer yourself. But in any case, to set this up, the large deviations from what would be expected based on sampling variation. So when you see stuff that's far off your expectations, that should provide evidence for the alternative hypothesis, right? So if your sample data is not a good fit with your expectations, you should have evidence that those were not good expectations. That would be evidence that you do not have a good fit. Oof. Okay. You can see it's called goodness of fit. Now it's on the slide as well, since we're evaluating how well observed data fit an expected distribution. How good is the fit? Whew, all right, sip of tea after that slide. That was a lot of stuff. All right, let's keep rolling dice for a minute here. Okay, anatomy of a test statistic. This is like looking at the engine of how this chi-square test works. So these are all technical details, but I think they're kind of interesting because it's noticeably more complicated than just the difference of two groups' proportions or just a proportion in one group. And so it gets a little funky. The general form of a test statistic is you've got your point estimate, you subtract away the value you've assumed about the population and divide that difference by a standard error of the point estimate. That's a number that, estimates how you expect whatever parameter you're working with to vary from sample to sample. So yeah, Yeah, those bullets say what I just said in different language. Okay, so same ideas help here, but it's just more complicated because now the point estimate is trickier. We're talking about multiple groups, not just two. The null value, how do you find a null value for 6 groups expectations? It's kind of funky. So we'll just show you what nerds came up with, like monstrous nerds from the early part of the 20th century. Chi-square statistic. Here we go. All right. When dealing with counts and investigating how far the observed counts are from expected counts, researchers use, and they're saying a new test statistic. It's new in this section to us in the textbook, but again, developed over 100 years ago. It's not brand new, called the chi-square statistic. Oh, chi is a hard number to read if you're not familiar with the Greek alphabet. Like it looks just kind of like an X on the slide there, unless you focus your eyeballs closely on how it's shaped. I'm going to underline the whole phrase there to draw your attention to see how the letter chi, it's kind of like a Y, but instead of just one tail, when you write a Y like this, I don't have a pen, but instead of one tail, it's like it's like 2 tails that are crossed. You know what I mean? Like a Y with 2 tails, or like an X that fell down to the position of a Y, like an X that slipped down to have tails instead of just sitting on the pen personship is challenging. It's hard. Greek pen personship. In any case, people often read it X squared. Don't judge anyone who does that, but it's the Greek letter chi, and if your eyeballs start to recognize it, that's great. Since my keyboard doesn't have a Greek alphabet, I always type it CHI in my notes. I do if I'm doing handwritten notes, I'm nerdy enough to have bothered to have a math teacher who cared if I write it correctly, so I've learned that. But if it looks like X in your notes, but it's chi-square, you're still good. All right, chi-square statistic. Look at that formula. Whew, okay, there's some shorthand there. Let's start with this. K is the total number of cells. What they mean is however many categories we're using to count stuff. So in Labby's example, there's 6 sides of the dice. So there's 6 kind of rows there in his data set. That's 6 cells of observation. Okay. O is the first letter of observation or observed count. Okay. And E is the first letter of expectation or expected count. So the idea here is for each, let's just look at this one. For each of your outcomes, so here's the first row of Labby's data set. You've got an observed count. There's the actual 53,222 times the guy counted the face of the dice value 1, that face. Subtract away the expected number that Tori calculated earlier for us, 52,612. That's a complicated calculation already just because the numbers are big. Square the difference. So there's the O minus E squared, and then divide through by the expected count. And see what they're doing there? They're getting some number that takes, well, at least how far apart your observation and expectation are. That's subtraction. The squaring makes sure it's positive and makes little differences less important and big differences more important. Kind of a nerdy way of that statisticians like squaring stuff instead of just ignoring signs for technical reasons. But then when you divide through by the expectation, you do that because we're kind of assuming that things are fair. So that makes that like the world in which you calculate this number is standardizing things to the expectation. How far from observations are from expectations, standardized by the expectations. So that produces numbers. When you look down the faces of the dice, of course, all the observed values are going to be different. So each dice face gets back a number from that little formula that is, smallish. They're not huge numbers. The face 3, the observed count was pretty dang close to the expected count. And the little, that's called a chi-square statistic, what's it called? It's like a contributor. We're gonna add up all these little numbers out here on this end of this. All of them come up. Yeah, so the biggest difference is 6 was the furthest from expectations, so it gets an 8 and 61/100. The littlest difference from expectations was 3, it gets a 41/100. And then for the full chi-square test statistic, if I go look back a slide, just we're gonna add up all of those. There's that summation symbol to add up these contributions to the chi-square statistic. Bam, 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 6 sides of the die, 6 contributions, add them up. And that number, 24 and 73/100 down there in that lowest right-hand zone of that big table of values is the chi-square test statistic that bad guys like Weldon developed in the early part of the 20th century for this kind of calculation. Whew. And you'll notice something that's nice in the days before computers. I mean, this is a wild experiment to think about, but because the numbers are so huge, but there's this nice double check. Your expected values, they better match when you add them all up, your observed values. That's always going to have to be true, or else the whole thing's just crazy. Or not crazy, but silly. Because if you already, they don't match, then you already shouldn't really be doing the hypothesis test. Sometimes they might be off by like some rounding stuff because of the way the expectations get calculated, but only off by 1 or 2, something like that. Okay, there's your chi-square test statistic. It's like 3 minutes till 10. You want to just talk about one little y-square of the values and then have a little break? Okay, yeah, there's a lot here. So y-square these values, I mentioned a couple of things. Squaring differences, like between the observed counts and expected counts here, does 2 things that statisticians like, that are cool for analysis. Everything's positive, so now we can talk about how far off rather than being above or below, so there's no more negative numbers there. And I mentioned it before, but the bigger differences end up having a bigger impact on the statistic. Like the furthest off number was face 6, and it gets the biggest contribution to the total here. Can you see what the chi-square statistic value would be if everything played out perfectly? If the observations were exactly equal to expectations, yeah, it'd be 0 because every difference would be 0. So when you do all this work and you get a number very close to 0, a small number, you get basically no evidence against the null hypothesis of things matching because they're dang close. The bigger the number gets, the stronger the evidence gets against the null hypothesis. Yeah.
Like as far as a wording, like doing like the whole paragraph.
Basically, yeah, and like this here, yes, but this part here, the chi-square statistic, this chunk is like we're still pre-p-value, right? We're still in the world of like the z from the last couple of sections, right? The z test statistic was all about standard errors away from expectations. The chi-square test statistic, it's actually a little weirder and more complicated, but the p-value that we get when we're all done will have the same meaning with respect to our hypotheses. So all of this complicated stuff in the middle is like showing us the tail of how we get to our p-value, which will have the exact same analytical value as it did in the example we talked about at the beginning of class. Yeah, it works when you have more than 2 categories, because if you just had 2 categories, it would be a difference of proportions. So like once you get more than 2 categories where you have counts you care about and expect things, this is a useful technique. And we'll talk about all that when we do this in more detail with the conditions, right? So yeah, you're looking right ahead to some good stuff. That's what we're going to talk about after the break. Last thing on this slide, where do we see this squaring in statistics? It pops up again and again, but the most common place is that standard deviation calculation, like all the way back in stats 1 for numerical data. Standard deviation of a numerical data set involves different squares of differences and an average depending on how you take it for samples or populations and a root. That root mean square this, anytime you've got these numbers that are, there's a square and a difference, you can tell statisticians were involved, and there's interesting analytical reasons for that that I've only seen well explained in one book. But like the explanation takes like 45 minutes and it uses a really cool example. So it's a little too technical for us unless someone really cares. And also the book is like buried in my basement in a box that it got put in a box like 10 years ago for life reasons. But if you ever want to know, I can tell you the book. It's a good one. It's an inexpensive stats book from like the 80s, I think, or the 70s that's still in print, in part because it gives clear, plain language explanations of some of the technical stuff. And it was written at like the level of like people who are going to be engineering students, maybe in like the 80s. But like, so they're all nerdy enough to like do all this stuff by hand. Nowadays, anyone who's nerdy enough to know like spreadsheets, like to know how to use like Excel or Sheets to do calculations quickly, I could wander through that book and not get hung up on calculations because I could set them up in a spreadsheet and go, oh, now I see how that works. Why, you smart person from the 80s. But so old textbooks aren't all useless. Some of them are cool and they hold value. Just like good novels from the past. If it's really wonderful, people will still get something out of it. So sorry, there's only like 3 good math and stats textbooks ever written. Maybe it has something to do with all the monsters who were involved, the jerks who, I mean, the first probability textbook ever written was written by, which one was it? I think it was Galton. I think it was Galton, and it's called Probability, the Foundation for Eugenics. Like the title is bad, and like just trying to read his weird racist screed that to him just sounds like scientific niceness and smartness as a horrible monster. It's wild. And of course, it's available for free online to any modern racist who wants to develop the ideas. Ew, ew. In any case, let's take our break. We'll be back after the break. Let's get back to our slide so we don't forget which one it is. Yeah, we'll start there. We'll be back here at 14 minutes past the hour. Great. Ew. Oh, sorry. I just like a pleasant, relaxing home screen for the break.
المصلين الذين هم يراءون عن صلاتهم ساهون ويمنعون هم يراءون ويمنعون الماعون.
All right, we're back. We're back. Back we are. Lots of mellowness here in Sylvania campus, all muted to not distract you out there in the world of Labby's Dice. And by mellowness, I mean me whining and complaining about my social life and personal history. Thank you for listening, kind people. All right, we talked about this technical detail right before the break. Oh, there's one of my best dice images that I found. Look at that. Beautiful. What a mix. Look at all those great dice. Say what? Oh, the interview. Great reminder. Yes. Before we talk in more detail about the chi-square distribution, let's look at that thing we skipped. The thing we skipped back in content. It's just a short little set of guidelines for our project. So if you go down to the project module, we talked in detail about project 1 interview subject last class. Ideally, this is something you could wrap up over the weekend, thinking of someone, contacting them, and getting a time set up to talk to them. Even if you don't have that last step of like having the contact made and your schedule set, you can, if you want to get it something to me by next week, you can say, I want to talk to this person, though they haven't responded yet to me reaching out to them. Like you can just give me a progress report for project part 1, your subject, and your questions. As soon as you have a good idea who you're talking to, you can write them up and get them back to me. And next Wednesday, I think is very reasonable for that. Again, if you have questions about what kind of questions are good or what I expect for that assignment, either check the very end of our last YouTube video or just ask me and we'll talk about it again. But for today, the interview guidelines, this is just like before I made the individual, you can see all the stuff is here in one doc for the first chunk of the interview. So all the stuff that's on there describing things. These little guidelines at the top, though, are all I wanted to talk about today. So just a short little set of things, not complicated. Let me just make them a little, oh, can I make them bigger? Bigger? Oh, no, I'm not in the right, hold on. Gotta get back into my PCC account to do this. Wait. I meant my, sorry, I meant my my PCC Google account. There we go. Continue there, get that, close that, open it up again. Why did I end up back at this page? I don't know. Go back here to our class. Go back where I was in content. Open the guidelines doc again, and now I can actually blow it up so I can read it out loud with my eyeballs not strained. All right, there's our guidelines. You know, this is a good one to type up just because I'm going to read them all and try to give you feedback. So it'll just eliminate any handwriting issues for my eyeballs. Homework, of course, and exam work. I'll always take the work with my eyeballs. So your homework and your exam work, handwriting or typing is good. But here, typing does help me get people feedback more quickly and get more out of what you're sharing with me because I can process it slightly better. You know, as you're writing up your responses to the various prompts that I share in these various parts of the work, just use, you know, original, complete thoughts. That's how I describe just your own style, but not like a one-word answer and stuff like that. But just, you know, blah, 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 blah in your style. So that can be sentences or paragraphs or combinations depending on how wordy or how not wordy your style is. Sorry again for being slow on getting you started with guidelines for the interview. Ideally, there's someone already in your mind, having just gotten the idea in your mind, who's an interesting person, either in your career field of interest or who is on your kind of academic world path that you're on right now. That's anyone who is in the working world that has a job you like or are interested in, who you might already know is ideal because they're easy to reach out to. Like people have reached out to family members, friends, current coworkers are popular there. Or if you're on an academic path and you don't, like, say you're heading for a psychology degree and you don't know like a research psychologist out there in the field world, you've got all these professors who you've worked with and teachers before. Anyone who was cool or is cool, you can reach out to for the project. So anyone who comes to mind, hey, welcome. Just anytime you want to do an interview, keeping a record is ideal. You could do your interview in any format, you know, in person, online via Zoom or any other online system. You can do it, you can use email and email your questions and they can type their responses to you. Anything else, you can telephones interview if you're a telephone type. Any combination of those works. But of course, take some notes if you like, but if you ask your interview subject if they're comfortable with a recording, especially if you're doing like a video chat or a telephone call, there's so many awesome automatic easy ways to record things nowadays to give you free notes on what you learn, and it's just cool. So cell phones have that technology. If you need support with any of that, let me know. Oh, and the last bullet was from, you know, I think I typed that one up 2 years ago. So it's about just paying attention to community health, although it is the winter right now. So if you get a cold or your subject has a cold, take that into account. And of course, we can always wiggle things around with flexibility on my end if that just delays things in any way for anybody, right? But those are the simple guidelines, straightforward. And then again, just the bonus reminder of going through the guidelines is as you're getting into your after class today, in your heart, mind, and body, just sort of focus yourself on, okay, if I haven't focused yet, who would I want to interview, and think about it seriously. Today, if you haven't sent a contact out to someone yet, I would recommend sending it out today. And that way, hopefully you'll get some word back today or tomorrow, or maybe on Monday. And so you can write up the quick thing for me by next class on Tuesday. That would be the dream. Of course, if there's delays in there, you can write up your progress toward that for me and share with me on Tuesday and just let me know where you're at. Sound good? Awesome. Okay, great. Any questions about this stuff while we're here? Because they're always good. Oh, make sure you can see both of the stuff to do for next week. Subjects up at the top, questions down here at the bottom. Any questions for me about anything? not in the room, I can see that, but I'll just give it a second. I'll look back at the chat after we navigate back toward our slides. So any interview questions, ask me today if you're outside this room with us. And now back to our regular scheduled dice rolling experiment. Oops. There we go. Bang. Beautiful dice. People love dice. I mean, I love dice. Yahtzee. I love Yahtzee is what I need to say. It's kind of cool that my last name is Yutz, Yutzi, Yahtzee. That's just luck. And it's like my family's favorite game. Just luck. In any case, in order to determine if the chi-square statistic we calculated is considered unusually high in light of our null hypothesis. So like, remember, if it's close to 0, there's very little evidence that there's a difference between observations and expectations. There's little evidence that it's not a good fit. The bigger the number gets, the stronger that evidence gets. But to figure that out, what probability people needed was a distribution of the statistic, a probability distribution. For the simpler situations we had before, we could use the normal probability curve to talk about one proportion or the difference in two proportions, that familiar bell curve. Here, there was some work to do to figure out how that works. And it's called, clever name, the chi-square distribution. And it has one parameter for drawing the shape of the distribution called degrees of freedom. And let me just show you what it looks like in, let's look at it. Well, there's a slide here with some pictures, but let's just look at the GeoGebra version as well, because it's kind of cool to get a sense of not just a picture on a slide made by a computer, but how it's going to look to us as we work with it day to day. Yeah, I'll head back to our course page. My favorite GeoGebra path now is the one that you all share with me in our links. Oh, that's teacher view. Blech, that's horrible looking. Look at all that boring extra detail. It's bad. Okay, back in our course, under the links, there we go. Our lovely link to our graphing calculator GeoGebra Classic. No thanks. When we land here, anytime we want to work with the probability distributions, or of course, calculations for confidence intervals or hypothesis testing, we use the probability calculator. If your device's screen is big like mine, and you've got a big window, you'll see all the options there on the screen, probability for me. If your device's screen is small or your window is small, you might not see that list there. If this is still new to you, the reminder is that little GeoGebra logo, perspectives, is that little list of options. Probabilities right there as well. If there's more garbage on the screen than you want, you can also try that home view, and you can turn off other stuff if it's got stuff hanging out that you don't want to see. Okay, when we land here, well, they just said we need a distribution, right? So we're at the right place. It's a probability calculator. We're on the distribution side. And if this is a new tool to you, the distribution list is right there to choose what you like. We'll meet the student distribution in the next chapter of our textbook. But here's the chi-square distribution. When you tap it, it's also a smooth curve, unimodal. Stats 1 quiz. Is it symmetric or skewed? Skewed. Which direction? Yeah. Skewness, the way I think of it, we just talked about it in stats 1 yesterday, is if you look at like oops, that's not the tool I thought I had. I want like a highlighter. If you look at the part of a picture that is symmetric, so this, I'm seeing this is the peak, goes down quickly that way. If I just imagine that the same here, skewness is where if there's more stuff off in one direction, that's your skewness. So boom, skewed to the right. Yeah, you got it. And as they just said on the slide, clean up my ugly stuff there. There's only one number you need to draw the curve. It's called degrees of freedom. So it's just a value. That's different than the normal distribution, where we would have to tell it a mean to get the center and a standard deviation to get how spread out it was. Here, the the degrees of freedom number ends up determining both the center of I guess the weight of the distribution is its mean or mu. Notice that degrees of freedom 6, at 6 is where the balance of that skewed right mess of probability would be. And then the standard deviation, it can be measured in a skewed situation as well. It's just a complicated number that I don't know how they calculate, but it's got one. So they're there if you ever, but you're not going to need those for day-to-day work. They're just interesting facets of the distribution. Let's peek back at the slide. And so they're just saying degrees of freedom, which of the following is false? As degrees of freedom increases. Oh, okay, look at that. Degrees of freedom 2, you can see it's super duper skewed to the right. It doesn't have that like coming down toward 0 like the one we just saw in GeoGebra. I think we can switch it over here. Now you can always change degrees of freedom as you like. Yep, the drawing just looks not quite as steep as the one on the slides because of the shape of the screen. They bump it up to degrees of freedom 4 to get that dashed green. You know, it looks more like our degrees of freedom 6 one that we saw in GeoGebra. And then they bump it up to degrees of freedom 9. Gets you know, they always have to have the same area under them because they're probability curves. So as degrees of freedom is increasing, well, let's just take each of these. Let's go A, B, and C. Let's do true or false for each of them. That way we don't have to search through to answer the question too carefully. A, the center of the chi-squared distribution increases as degrees of freedom increases. Yes or no? Center meaning like where it would balance out as weight. Yeah, true. So like, and if you want to see it in numbers over here in GeoGebra, focus on the mean. That's the balance point of the picture. So for degrees of freedom 2, it's at 2. For degrees of freedom 4, it's at 4. For degrees of freedom, I think it was 9, it's at 9. The curve is designed for that to be true. It's the way it's drawn and created, it sets the mean at the degrees of freedom parameter. Cool. Okay. The variability of the chi-squared distribution increases as degrees of freedom increases. Does it look like it's more spread out? Is the blue one, is the green one more spread out than the blue one? And the pinkish one more spread out than the green one and the blue one? Yeah. And we can just peek back into GeoGebra to double check the numbers. Let's go back to degrees of freedom 2. The standard deviation there, it's 2. No fancy number. So whatever fancy calculation happens for the lowest degrees of freedom you can set, which is 2, it's nice, 2, 2. But then when we go up to 4, yeah, it's 2 and a little more than 8/10, so it's increased. When we go up to 9, that standard deviation sigma is now at 4 and more than 2/10. So yeah, it's increasing with degrees of freedom. Well, we've done some process of elimination. The false one is C. So it's got to be false. We've run out of other things. The shape of the chi-squared distribution isn't getting more skewed with degrees of freedom. It's getting less skewed, right? It's pretty clear that the degrees of freedom 9 pink dotted curve looks a lot more like a bell curve than that pointy, completely right skewed degrees of freedom 2 curve. Yay, chi-squared distribution. So cute. Okay, now back to the dice. We've looked at this complicated statistic. Oh, sorry, wait. The slides skipped something important. What are these numbers? 2, 4, 6, 8, 10, 12. Did I tell you? Did the slides tell you? Those are chi-squared statistic values. So see here at degrees of freedom 9, the way this curve works, to get a p-value, you always look at the area above your chi-square statistic. So, you know, and I said before, if your chi-square statistic is close to 0, there's no difference between the expectations and observations, and the p-value you get back is a solid 1 or a 100% chance you'd see these data under those assumptions because it's all the same. The bigger the number gets, the like if you had chi-square statistic in this picture of say 30, I'll just type in a 30 because I can see it out there, far out there past the main part of the graph. There's still a tiny p-value because it's, slowly approaching that x-axis, or sorry, that chi-square axis. But it's a super duper low p-value when you get a chi-square statistic that takes you out into that right tail, the skewed part. Okay, so just wanted to make sure that's said before we talk more. The distributions, the probability ones, it's always like that probability, the test statistic is always on the axis. Whether it's a z or a chi-squared, or next chapter we'll see t and f. I think that's all we're going to see this quarter. What am I doing? Okay, so do our data, or does Labby's data, provide convincing evidence of an inconsistency between his observed and expected counts of dice rolls? They've cut and pasted the hypotheses from before. The short version of the null hypothesis: expectations and observations match. That is, his dice are fair, and this is random variation. The alternative hypothesis is, the observations do not match or fit expectations, so we have evidence the dice are unfair, or at least slightly unfair. Chi-square test statistic is 24 and 67/100ths. Though we still don't know which degrees of freedom to use for this particular experiment, just because they haven't told us it on the slides yet. So yeah, all we need is the degrees of freedom, DF, and we can calculate that tail area, that p-value I was just exampling a little bit to get a decision about these hypotheses. Let's go. Ooh, dang. 5 dice. Straight up Yahtzee. Straight up Yahtzee. I like this degrees of freedom formula. Totally relaxing. Whatever number of categories you're looking at, just subtract 1 from that for your degrees of freedom. We got 6 sides of the dice. So how many degrees of freedom are there? Yeah, 5. 1 less. And in this world, that'll make our probability curve specifically be this one. Degrees of freedom, 5. Super cool. Okay. There we go. For Labby's dice outcomes, it says on the slides what we're talking about. Degrees of freedom must be 6 less 1 or 5. And I didn't delete this slide, even though I do not want you to look at the table of values for chi-square statistics. It's just a weird table because it's tricky. It's governed by degrees of freedom, which is good. But then because it can't guess, like they can't be guessing the exact values of the chi-squared statistic, because it could be like any number from 0 up, right? So what they did in the olden days before computers, they got the calculations done for the chi-squared statistics areas beyond certain chi-square values. They just pick the values. So 0.3, like see that 6.06, you could get that nowadays. You just be like, I'm here at degrees of freedom 5. I'm looking at the upper tail, and I've got 3/10 is my chi-square statistic. Wait, am I doing this wrong or right? Oh, hold on. I'm wrong. 3/10 is they're talking about this. If you want to have a statistic that is 3/10, that's your probability. Your chi-squared statistic can be no higher than 6.06. See that? So like that part of the table in olden times, that 606 was the chi-square stat that will get you back 3/10 of the area in the upper tail. And then they just have the numbers that'll get you back 3/10, 2/10, 1/10. there's the traditional significance level of 5%. So any chi-square statistic that's bigger than 11 and 7/100ths, see right here, 11 and 7/100ths. That'll get you 5% of the area out in the tail. Beyond that, you're going to have significant evidence at the 5% significance level that observations do not match expectations. And I forgot the exact chi-squared value from the experiment, but it was 20 something, right? Yeah, let's peek back together and double check all of our memories. 20 something. Yeah, 24 and 67/100ths. Awesome. So that's noticeably bigger. I can, in modern times, I can just type in my chi-squared statistic into the comparison there. So there's the chi-square spot, 24 and 67/100ths. The p-value here, we can't even see the statistic. It's off the screen, and it's just a tiny amount of area further out there. So, and it's because of the huge sample size that those little tiny practically boring differences get picked up as significant because there were thousands upon thousands upon thousands of samples, dice rolls. 0002, and in the olden days before computers, the table in the back of the book just says, well, our number is bigger than 20 and 52/100ths. So we're going to have a p-value that has to be lower than 1,000. You know, kind of weird. I like better just knowing that our actual p-value is 2/10,000ths. It's that low, cool. So yeah, old-timey by hand calculation, it's there, but I would recommend, so you'll see in the textbook, because our textbook, whoever wrote it is old-timey enough to like these tables, they'll often describe their p-values in terms of ranges, like, because if your chi-square stat comes in between two of the values in the table, your p-value's in between two of the areas up at the top. The olden days. Can we please leave them behind, especially all the eugenics crap? Pardon me. Finding a p, I mean, no, don't pardon me. That's a good idea. We could leave all that crap behind. But how? How do we do it? Finding a p-value, I just showed you how this calculation works live. Here's the slide. For some reason, my screen, maybe I had a small window when I was doing this and I made this slide so it looks kind of bad, but you can see I typed in my 20, oh, I made a mistake in this. I think what I did was I made a little mistake, but you type in your p-value, sorry, your chi-square statistic here, your p-value comes right back there. I can see the mistake I made on my slide. If you want to know how I got this, well, if you ever care how I got that wrong p-value, we can talk about it. Or sorry, this wrong statistic here, I can show you if you care, but if you don't care, it's not worth it. Oh, and then, but more importantly, we don't have to do all those calculations for the chi-square statistic. If you have the raw numbers, you can just use GeoGebra's hypothesis testing routine to quickly calculate the p-value and the test statistic. Here's why the test statistic's a little bit different. The one that we have from the slides, when they calculated it back on this slide, big table of numbers, remember that one? See how they rounded them all off to the hundredths right here? All that rounding? Well, this 2473, see, and it's like, why is it 2467? Is it like a typo? I don't know, whatever happened. But when you use a computer for this, in GeoGebra on the statistics side where we have hypothesis testing, so put a little heart there, for this is the way to really get this done quickly and accurately. When you go to the statistics land, they're right there in our options, all the way down below the means and proportions and tests and estimates for those different combinations. There's our friend, the goodness of fit test, right there waiting for us, like a little pal. Of course, I don't want to try to type in all of Labby's values here because that's a lot of typing. The crucial thing to know when you're setting this up is Don't like type in 50 something thousand and something here and then go, oh yeah, there's 6 sides of the dice and I've got to set up the rows. Be sure to set up the rows first, because when you change the row number, it erases everything you've got in the table. Just from experience, I know that can be annoying if the numbers are annoying to type. But I think most of our examples that we'll see in homework or on exams, it's like 3 to 5 categories usually. This test though, I mean, our computer goes up to 12 rows. It gets more and more wild as you add more and more rows. Back on the slides, you can see when I typed in Labby's observed counts carefully and Labby's expected count value repeatedly. I also labeled the dice, the values from the sides of the dice. Those blue labels are completely optional. They don't affect the calculation, but that can be useful for notes, like if you're taking a screenshot for your notes. And you'll see there's a little more 4 decimal accuracy on that chi-squared number, 247,315, but the same p-value we got 0.002. Looks great. Output comes. Reminder that what the degrees of freedom is, if you want to look at the chi-square picture, you can always switch over to the distribution and look at how it looks. Kind of cool. Yay, yay. Fast, straightforward calculations. Yeah, yay to just set that up here and you get your p-value. Good old computer. I mean, good new computers, good old computers. They're old now. They're older than most of us in this classroom, age-wise. I mean, as a technology. Okay, so our slides makers calculated a p-value less than 1,000th because they used the table in their book. We have the p-value 2/10,000ths, or 0.02% low. At the 5% significance level, what's our conclusion for this hypothesis test? Let's just take them one step at a time. Are we going to reject the null or fail to reject the null? P-value is 0.02%. Very low. Under our assumption that things all match up here, our data set looks ridiculously unlikely. So what are we going to do with the assumption? Reject it or oh, there's a chat. It says reject. Is that giving people confidence? It's reject. P is low. The null must go. Simple rhyme. So let's get rid of the second 2 options. Bye-bye. We're not failing to reject. We are rejecting. That gives us evidence, significant evidence in a statistical sense, that Labby's dice are fair, A, or unfair, B. The null was that the dice are they didn't put it on the slide. The null was the dice are fair. So we just rejected that. So we have evidence that his dice in a statistical sense are unfair. B, as Quincy has in the chat. And we talked way back at the beginning that, big deal. It's just a little bit off in terms of these huge numbers. But because the numbers are so huge, huge sample sizes will make small proportional differences into statistically significant differences, even if we don't care that our Yahtzee dice are just slightly out of whack. I hope he did. I should read the whole study from Labby just to see if he used official Yahtzee dice, because those are the best ones, right? Yeah. It's a lot of dice. We really diced. All right. That's the fully complicated, long example. I think there might even be a couple other little bonus notes here. Turns out, some dice facts. Here we go. The 1-6 axis. So, the distance from 1 to 6 on the dice that Labby used is consistently shorter than the other 2 axes of the dice, from side 2 to side 5 and from side 3 to side 4. This supports the hypothesis that the faces with 1 and 6 pips are larger than the other faces? If you think about that geometrically for a second, sketch something on in your notes, a die, it might make a little sense. No pressure. It's just a geometric explanation for why this makes sense. Pearson's claim that 5s and 6 appear more often due to the carved out pips is not supported by these data. Hold on. Did they use the same dice? I don't know. Unless they have Pearson, oh, that's a different monster than Weldon, the guy we talked about at the beginning. Unless they have the same dice, they should not be thinking about talking about comparing Labby's result with his modern Monopoly dice to Pearson's and Weldon's results with their 19th century, gambling dice, right? Good news for modern dice likers. Dice used in casinos nowadays have flush faces. They're flat on all sides. And the pips, the markings, while they are like, it's clear red plastic for the body of the die, and the pips, the marks are also plastic, though they're supposed to be the same density, and the dice are supposed to be perfect cubes. Hence, they're supposed to be perfectly fair. So if you get fancy dice, you can get the fair ones. Why would casinos want perfectly fair dice? It's simpler than that. What do casinos want? Money from gamblers. And that's the more the probabilities play out as expected, the more money the casino makes. The games are designed to make the casino money when they're fair. So if they had bad dice, the casino might be the one who loses money if they're not coming up the way the casino believes they should. Have fun gambling. Don't gamble more than you can afford to lose. If you enjoy losing your money or the occasional thrill of winning some, view it as a game and never gamble more than you're happy to lose. All right, there's the p-value, the little picture. I think of the shape there, that chi-square distribution shape. It's like every time we set up a hypothesis test, the curve's shape is like we've just drawn a picture of the universe of the null hypothesis probabilities, right? We make an assumption about the world, and then we get a probability picture of how likely sample data would be as it varies in that world of the null. The p-value, again, is going to be cut off by sample data, so it relates the likelihood of our sample stuff showing up in the world of our assumption. And in this world, as the p-value gets bigger and bigger, we get smaller and smaller p-values, hence stronger and stronger evidence against the assumption that we have good fit between observations and expectations. All right, cool. Yay, p-value. Like, did Labby ever become a professor? And then one of his graduate students was like, "Well, did you try the casino? Nice." So that's my statistics student voice, not anybody else's. That's how I would talk if I was the student. But I don't know. Yeah, but if anybody wanted to do the follow-up study with the supposedly perfectly fair dice, that would be cool. But again, it's just those little tiny differences, right? Those very small differences. What I would like to see is if someone, like using casino dice, whatever, Yahtzee dice, dice from a few board games that people like, that are just slightly different. It would be cool to see like what's the real variation, dice to dice, for these different designs. And who cares? Like, do we care? Do we care if we're not a casino? We just want to win, if we just want to make it to the Yahtzee Yutz family records, recorded in the top of the box on the inside in pencil. My grandfather, the great high score holder of Yahtzee. Rest in peace, Grandpa. Yahtzee to you. Oh, well, we're out of time. It's 10:51. It's 10:51. We never got to the conditions for the chi-square test, just to give you a peek at them, because you basically have all the tools to start the homework, but it's always independence, right? We always need independent data for everything we do all quarter. So that just means that none of the counts or the things you're counting have any impact on any others in the different categories directly. So anything in the sample, random sampling guarantees that. Sample size is just slightly different thing to check than it was in the world of proportions. You look at the expected counts. So oftentimes they have to be calculated, like they were for the dice. And as long as those are all 5 or more, this thing works well. And that's how it works. And degrees of freedom has to be bigger than 1, because yeah, this only makes sense for more than 2 groups. So cool. Degrees of freedom 2 and up are good for this thing to work. And the bonus note is for every hypothesis test, if you don't check all the conditions and make sure they're met, you can get bad results. You can be wrong in your conclusion because the data set's just not suitable for that kind of analysis. All right, cool. And we'll start off next class with a bonus example, looking at some election results from a now historical Iranian election, 2009. Right? Yeah. And I'll tell you, I went online and got some photos of the politicians and added them to the thing. I added them in there, and you'll see next time. Or if you want to preview who I'm jealous of hair-wise on planet Earth. It's, to be honest, it's Iranian politicians from 2009. Great hair. These guys are handsome. All right. See you next week. Interview, subject, get that going in your mind, heart, and body. Get your ideas together. Let me know what they are. And for your write-up for that first chunk, and I'll have something interesting to read next week. Yeah, rad. All right. Fare thee well, y'all. I can't